Welcome back to the new video that is planned for the fundamentals of light and optical modulations. So in this section, we will discuss regarding the optical communications and properties of light. So let's start with the little bit basics of optical communication. Now this optical communication where we are basically converting our data to light, and that will be sent or propagated in the medium where this light can travel. So it can be a glass fiber or a plastic fiber. So that we will be discussing in the upcoming videos. Now in this we will first discuss regarding what are the steps that is involved in this optical communication. Okay, so first let's understand what is optical communication. It is nothing but a process. So optical communication is the process of converting your electrical signal into the modulated light signals, that is transmitting them through the optical fiber across a given distance. So this can be some distance. So let's say it's for 10 kilometers. Now there are multiple steps that is involved. Okay, let me just erase this. Now what are the steps that is involved in optical communication? So the optical communication, in this let's understand first. So your input that is coming here, it is the electrical signal that is coming. So this is your input. Now that will first go to your transmitter. Then we have the fiber optics that is connected. Okay, then we have the receiver, post which that is your output. That again it will get converted into electrical, since the input was electrical signal. Okay, so the step number one, that is nothing but that is data originates as a electrical signal or electrical digital signal into the network equipment, that is equipment number one. Now here the optical transmitter, that is the second unit, that converts your electrical signals into modulated light signals. Then it will be launched into your fiber optics. Okay, so this is your fiber that is laid across the distance for the transmission across them. Now next is the next unit that we have is the receiver. Okay, so the receiver receives the incoming light and converts it back into the electrical signal. So this is the whole process. Now your transmitter, it can be your laser modulator. Then in the receiver section, this can be your photodetector. So later part of the video I will discuss regarding this. Now let's come into the agenda that I have set for this particular video. So in this we will discuss regarding what is basically the light. Okay, now let me just add another slide here. Okay, now what is light? Light is nothing but it is a form of electromagnetic radiation, that is, now this has a particular wavelength or frequency of a particular range. Okay, so in the optical communication, the optical spectrum, okay, electromagnetic spectrum that we have, this can be your ultraviolet region, or it can be your IR region. Okay, Now what we use for the optical communication, that is approximately, it ranges from your 850 nanometer to 1675 nanometer. So the wavelength range is between this range. Now I have a slide that explains that. Okay. So this nanometer range, for those who are new to this is nothing but it's a billionth of a meter. So it can be written as 10 to the power minus 9 of a meter. Okay. So when I tell 850 nanometer, that is 850 into 10 times minus 9 meter. Okay. Now when we have to explain someone regarding what is a light, okay, when someone is new, then we can say that a light is a form of electromagnetic radiation. So this is a electromagnetic radiation. This is something similar to your radio waves or X-rays, but with much shorter wavelength. So in optical communication, the near IR range spectrum is predominantly used. That is around 850 nanometer that I said earlier, and around 1260 nanometers till 1625 nanometers. Later I will discuss regarding different types of spectrum that is used for fiber communications. Now this later part we will discuss regarding that light also exhibit both wave behavior as well as particle behavior. The key property of light, when we discuss that, is basically your wavelength, or this can also be converted into frequencies. We have amplitude, we have phase. So one by one we will discuss regarding these things. Then we also talk about polarization of light. Now when we are propagating through the optical fiber, okay, so when any light that propagates through the optical fiber, okay, now this is guided inside the fiber within the core with the property we call at as a TIR, or total internal reflection. Okay, so when incoming light comes, it passes through the core of the fiber with minimum attenuation for it to be transmitted over long distance. Okay, so when the distance is long, over hundreds of kilometers, then it has to have a minimal attenuation. Now these fundamental concepts that I just use the words, we will discuss in detail. Okay, now how they are generated, how they are modulated and detected in the modern networks, so we'll discuss one by one. Okay, now coming to the properties of light. Okay, let me just add another slide. Okay, now this was what I was talking to you about. Now these are the range that we use for the communication, that ultraviolet, visible, as well as near IR range. Okay, so that lies between this spectrum, that is 850 nanometer to 1675 nanometers. Okay, now in the properties of light, so these, when we define something called as a wavelength. So what is a wavelength? This basically is the length of the cycle when the light travels, when it completes one entire wave. Okay, so that is your wavelength. Frequency is nothing but per second. Okay, so frequency is c by lambda, where c is your speed of light in vacuum. Similarly, when we have what is amplitude of light, so when you complete the wave, so this height of the wave is known as the light intensity or the amplitude. So this represents your intensity of the light. Then we have the phase. Okay, so position of the point where it is lying inside this entire wave on complete cycle of the wave, the point where it lies. So that is nothing but your phase. Then we have the polarization. So we have multiple components of the light. Okay, so we have XYZ component, and that orientation of the electric field, whether it is a linear or circular or electrical, so that is represented by something called as a polarization. Now all these properties, all 5 properties that you see here, so together they are representing all the information that is defined for the light. Okay, let me just go to the next slide. Okay, let me just take another empty slide and explain what is this different components, or when we talk about all the 5 components in a single slide. Okay, so let me just draw a line. Okay, let me take a different color. Okay, another color. Okay, so the orientation of light, okay, let me just color it differently so that it can be visible. Similarly for the, so this one, let me just tell as a Z component, this one as a X component, and the one which is perpendicular to it, this is as a Y component. Now this represents your, as I told earlier, this is the amplitude. Now one wave cycle from here to here. Okay, so this one is nothing but your wavelength. Okay, so this one cycle represents your wavelength. Now the vertical component, this one, this represents the phase. Okay, so and this we have the horizontal component. Now using this we can relate the previous all topics that we had discussed here. Okay, the wavelength, the frequency, that is per cycle, the amplitude, phase, and polarization. So the here I have taken the different component. One is the electrical component, magnetic component, and actual component, that is in the Z direction, actually where the light goes. So X and Y components are your electrical and magnetic component, and in the Z side your light travels. Okay, so once again I will just explain. Basically, mainly the confusing part will always remain how we discuss what we call as a phase and what we define as a polarization. Okay, so phase is nothing but this is the position of the point within the wave cycle. Okay, or the phase is the it is basically, it becomes critical in coherent optical system for encoding or detecting information that I talked earlier when we have the receiver side. Okay, so when I was explaining in the earlier slide before, so at the receiver side, how we detect that is according to the phase, we will come back to that later. Now when we discuss the polarization, it is nothing but the orientation of the light wave electrical field vector. Now as the light propagates, okay, so as I was telling you, it has both the electrical component as well as the magnetic component, and the field vector of the electric field vector as it propagates, that is represented with the polarization of the light. Okay, so this can be linear, or it can be circular, or it can be elliptical. So using this polarization management, and this is basically important for ensuring the optical as well as optimal signal quality. Okay, so this part I had already discussed, so that is explained in this slide. So basically your electrical input comes, it goes to the transmitter, where it is modulated along with your source. Now it goes to the fiber for the longer distance data sending. Then we have the photo detector at the receiver side. Then we have the again reconversion back to your electrical component. So what we have sent earlier, the electrical, again we at the receiver side also you have to receive the electrical signal. Okay. Now let's discuss regarding the different bands that we have. Okay, so these are nothing but the transmission bands that we have. So we call that by a different nomenclature. One is called as a O band. Now O band here, this is also expanded as a original band that ranges from your 1260 nanometers to 1360 nanometer. Then we have extended band, that is 1360 nanometer to 1460 nanometer. Then we have short band, that is 1460 nanometer to 1530 nanometer. Then we have the conventional band, that is C band, that is 1530 nanometer to 1565 nanometer. Then we have long band, that is 1565 to 1625 nanometer. Then we have ultra long band or U band, that is from 1625 nanometer to 1675 nanometers. Okay. Now as a note, I have also mentioned here that 850 nanometer is basically used for short reach multimode applications. Okay. Now these are as per your ITU-T standard. Now coming to the relationship between your wavelength and frequency. Okay. So earlier I had told you that frequency is nothing but C by lambda, and if you just inverse this formula, so lambda is equal to C by F. So they are inversely proportional. Now as the wavelength increases, frequency will decrease. Okay. So now if you just take one example, like for example, it is considered here if lambda is 1552.52 nanometer. Now how do I convert it into frequency? Okay. So using this formula, frequency is equal to C by lambda. So C is your speed of light in vacuum. Now that if you divide by 1552 nanometer, okay, that you will get around 1.9 terahertz. Okay. Sorry, 1.93 hertz. Now if you convert it into terahertz, it's 193 terahertz. Okay. Now here also the refractive index of the light is also considered in the glass, that is 1.46. Now let's go to the, now let's understand the main concept that we use, that is called as a decibel. Okay. Let me just go to full screen mode. Now decibel is a relative unit, okay, that is represented in small d and capital B. Okay. Now it is a logarithmic unit used for measurement and express the various optical parameters such as optical loss or gain or power. Okay. Now this is a 2 power level. Okay. dB is a absolute unit representing actual optical power. Okay. Now it is always with the reference of 1 milliwatt power. Now if you just see anything, how a loss or gain is represented, you can see it is in a logarithmic scale. So dB is nothing but 10 times log to the base 10 P out by P in. So here P in is nothing but your input power, and what is your output power. So let's say any optical power is entering here, so that is your P in, and this what is coming out of the system, that is your P out. Now P out by P in, that log 10 of that unit is will give you the dB. Okay. Now when another unit that we use in the optical communication is the attenuation coefficient. That is nothing but 10 by L, that is length of the fiber in kilometers. Again, log of 10 P in by P out. Now absolute power we always take as a 0 dBm, that is 1 milliwatt. So this is the reference point for the absolute optical power. Okay. Now there is a quick reference here, since it is all a logarithmic scale. We always consider, okay, we take minus 3 dB as a half power, minus 10 dB is 1/10 or 90% loss, or plus 3 dB as a double power. Now let me just give the recap of what we learned. Okay. So first we started with the optical communication, where how the light gets converted from electrical signal into modulated light signal, and it is sent through the fiber. Then we also saw the electromagnetic spectrum and what is their wavelength, frequency range, and different properties of light, like what is wavelength, what is frequency, amplitude, phase, and polarization, and what are the different bands that is defined by ITUT standard. Now that ranges from your 1260 nanometer all the way up till 1675 nanometer. And we also saw what are the units that is used for checking the properties of light, that is wavelength, frequency, and how they are uh, related to each other. Or so again I will repeat, they are inversely proportional, that is lambda is equal to C by F, or F is equal to C by lambda. Now the unit that we use for measurement of the loss, gain, or the power is always in either dB or dBm. Okay. So in the next section, I will discuss regarding what is